the number systems and the real number line. So a lot more definitions now, just still not a lot of real hardcore kind of computational math yet. We're just getting the lay of the land and getting our terminology down. The word set is very kind of all encompassing. A set is a collection of objects. So it's a bag of stuff. And those objects can really be anything. We're more concerned with sets of numbers, this being a math class, but they don't have to be. They can be letters or colors or shapes or whatever. We call those objects the elements of the set. So the stuff inside the bag is the elements of the set. Notation wise, we use, so those, what some people refer to as fancy brackets, are actually called braces. That's what we use to denote a set, so to enclose the elements of the set. So if I ask you for it, let's say, what is the set of natural numbers less than 5? I named it A for some reason. I didn't have to name it at all, but sometimes I want to name them. So you would list the natural numbers less than 5, which is just 1, 2, 3, 4. Remember, natural numbers, not 0. And then you would put that in braces to denote that it is, in fact, a set. Okay? And it's a finite set. It only has 4 elements in it. There's a unique set that we have to deal with sometimes. It's just called the empty set. Pretty obvious term. And you can write the empty set, or you can just write some braces with nothing in it. Or you can write this thing. So this is a 0 with a little diagonal slash through it. It just literally stands for the empty set, or sometimes you'll hear that called the null set. And sometimes you'll hear this symbol called the not symbol, but that's not as in N-O-U-G-H-T. So not means nothing, basically. All right, so now let's just deal with every kind of number we have, okay? And let's classify them. So that way, when I refer to something like the rational numbers in the future, you know what I mean, and you know that I mean a set, okay? So the one we've already defined is the natural numbers, and those are the counting numbers. So this is obviously an infinite set, and when we want to denote an infinite set, we use ellipses, right? The dot, dot, dot is called an ellipses. So you write 1, 2, 3, 4, and then a dot, 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 because any reasonable person would extrapolate from that you mean 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? You could very easily say, okay, I get what set you're going for there. Okay, so we just kind of build out from there. So those are the natural numbers. Maybe you know what an integer is, but it's important. An integer is any whole number, including negatives and 0. So there are the integers written in our new kind of set notation with the braces. Now it might look a little weird to you to have ellipses at the beginning and at the end, but it was important for me to write it like that. So the integers are the whole numbers, including negatives and 0. I should have said also including 0. So the dot, dot, dot indicates that like this list started way back there. So obviously, again, it's an infinite set that goes off in either direction. But there's a smallest natural number, and that's 1, but there's no smallest integer. So putting the ellipses on both sides just indicates that, yeah, it just keeps stretching out forever. And again, I think if you just list a couple terms like this, any reasonable person would conclude that, oh, you mean, you know, -5 is in here and -18, and also, you know, 1,000,000 is in here. And so any whole number, regardless of whether it's positive, negative, or 0. Okay, expanding once again to the rational numbers. So this is a little more involved of a definition. The rational numbers are numbers that can be written as P over Q, where P and Q are integers, and Q is not 0. And I think you should know why that is at this point. Dividing by 0 is the one really big just no-no in mathematics. You just can't do it. And it's not because just we say so. It's because it breaks the fundamental definition of what division means. So if you try it on your calculator or something, it crashes your calculator, right? It says error. Okay, so you do that, and you wouldn't try to put something over 0, but while we're defining stuff, we want to be specific. Okay, so when you hear the word rational in mathematics, just think ratio. Don't think rational as in like it makes more rational sense than anything else. Think ratio, right? P over Q is the ratio of P to Q. Because next we're going to talk about irrational numbers, and those ones aren't a ratio. They aren't a fraction. Okay, so any fraction, and once again, positive, negative, whatever, gets to be a rational number. But think about why that's more inclusive, because you could take any one of your integers, say 3, you could write 3 as 3 over 1, or you could write it as 6 over 2 or 9 over 3 or whatever. So technically, all the integers are included in the set of rational numbers. Okay, so here's some examples of rational numbers. Any fraction you can come up with, positive or negative, big or small, whatever, is a rational number. And then just making it clear, since, for example, 3 is 3 over 1, the set of integers is enclosed within the set of rational numbers. So that's called the subset. There's a word for that. Okay, so every integer is a rational number, but not every rational number is an integer, right? 2/3 is not an integer. Okay, so the naturals and the integers are all contained in that. And then if you have a decimal that either stops, so terminates means stops, like just think 1.5. Right, 1.5 is obviously a rational number because 1.5 is the same thing as 1.5 or 3/2. It's just a different way of writing it. And then if a decimal repeats, it's also a rational number. So for example, you might know that 0.3 repeating, right, 0.33333 is 1/3. Okay. So there are some examples. 2.5 is obviously a rational number because it's 2.5. 3.625 repeating, whatever fraction that happens to be. It's actually pretty tough to figure out what that is as a fraction if you don't know, so don't worry about it. But either way, it's a repeating decimal. Negative 0.6 repeating, maybe you know that 0.6 is repeating is 2/3. So negative 0.6 repeating is the same thing as negative 2/3. It's just a different way to write it, and obviously negative 2/3 is allowed to be a rational number. Okay, so repeating and terminating decimals are in here. They're in the set of rationals. Okay, so now it's like, well, isn't that everything? And the answer is, yeah, pretty much. So the only kind of number we haven't covered so far is called an irrational number. So let's talk about those. We don't really have to deal with those a lot yet in math, but they're important. And since we're on this topic, let's talk about it. All right, so every type of number you know about is a rational number except for these guys. So they're called irrational numbers, which once again just means that they can't be written as a fraction. It means this part here. Irrational means not a ratio. Okay, so they're infinite non-repeating decimals that can't be written as a fraction. So the place you've seen irrational numbers up to now in math is the most famous one. Hopefully you're all thinking right now the most famous irrational number is pi. Right? Pi is the ratio of a circle's circumference to its diameter. Or there's a million other ways to visualize pi, but usually pops up when circles pop up. So a rational number is like you couldn't just produce one because the decimal representation would never end, but they pop up in nature, right? They pop up in real life like pi does. There are many other famous ones throughout mathematics that just pop up in math, and they pop up in nature and science and stuff, so they get their own name. Okay, so pi, right, that's the pi symbol, that's the famous one, 3.14159, ... that will never end, right? So the pi is not a fraction. There's no fraction that equals pi. And then maybe another place you've seen one that's kind of a basic the way to get them is to do square roots of other numbers. So the square root of 2 is an irrational number, as is the square root of 3 and 5 and whatever else. Historically, that was the first number that was ever proven to be irrational, as far as we know, is the square root of 2. So go ahead and punch square root of 2 in your calculator, and you'll get 1.41 something, but either way, it will never end. Not rational. Okay, and then there's plenty other places, but we won't worry about that for now. Real numbers are the rationals combined. So the way we can depict real numbers or plot them is on something called a real number line, and forgive my freehand drawing here, but you've seen this before. You literally just draw a line. I like to draw arrows at the edges because it indicates that it keeps going forever. We put 0 kind of smack dab in the middle of it, and then that number is called the origin. It's kind of where everything else originates from. And then you can just kind of put hash marks for the numbers, 1, 2, 3, -1, -2, -3. So all the numbers live in this real number line somewhere, right? The number 1.5 lives in here somewhere. The number pi, let's do a 4. The number pi lives in here somewhere. It's a little mysterious as exactly where it lives, but it does. Okay, so all the rationals and irrationals live in here somewhere. And one use of this is to picture what's called inequalities, and that's just simply if I say something like, okay, 4 is greater than -2, you probably agree with me, but on the number line, 4 lies to the right of -2. So it's just a way of depicting that kind of thing. Your book uses it a lot more than I'm going to. So here's inequalities. Inequality just means instead of an equal sign, you have one of those little pointy signs that means something's greater than or less than or something like that. So I think you've seen this before. All right, so if you see the little rightward pointing caret sort of symbol, that means greater than. So 7 is greater than 5, right? I think that's something we can all agree on. Similarly, if the thing points the other way, you would read that as 5 is less than 7. So those two things really mean the same thing. They're just two different ways of writing it. So notice no matter what, though, the arrow points to the smaller number. So it opens towards the larger number. Okay, so however you remember that. If you have the little line under the greater than or less than symbol, that is inclusive. So that means greater than or equal to in that case. So, I can't say that, 7 is greater than or equal to 5 because it's not equal to 5. But if I have a number like x, I know we're not to x yet. But you know what x means. It just means any number. So if I tell you that x is a number that's bigger than or equal to 2, then, well, that's what that means. So the little line under it doesn't seem like it does a whole lot, but when we get farther in, it's going to be important that we're specific of whether it's, so this would be inclusive and this would be like exclusive. It excludes it, whereas this includes possibly 2. Absolute value, this is another important concept. So a number's absolute value written with the number in little bars like that. So A is my number, and it's written in little vertical bars. And the way I define it is the distance on the number line from the number to 0. So it's incredibly easy to compute a number's absolute value. But we have to understand the concept. And so I do like using the word distance. So the thing about a distance is that it's always positive. You would never say my house is -5 miles from here simply because your house is like 5 miles in the direction you're not facing. So let me draw another number line. Here's 0. Here's like -3. So the distance from -3 to 0 is 3. Now the distance from 3 to 0 is also 3. So those two numbers have the same absolute value. It's as simple as that. The absolute value of -3 is 3. And the absolute value of 3 is 3. So it's always positive. In the case of positive numbers, the number's absolute value is the same thing as the number itself. So the absolute value of 5 is 5 because it's 5 away from 0. But the absolute value of negative numbers is, well, you just switch it to positive. Okay, so that's it. So if I put those little absolute value bars around a negative number, that just essentially takes away the negative sign. And if I do it to a positive number, it does nothing. Like that. So 5 is 5 away from 0, so the absolute value of any positive number is just the same thing as the number itself. Okay, so that is a very important concept moving forward, even though it's a simple concept. So I think if you just remember, think of the word distance when you see those absolute values, you'll remember that it's a distance from 0, so it's just always positive. So all it really ever does for now is turns negative numbers positive. Okay, thank you.